Here in this video, we will be deriving laws of reflection. We will be using wave theory of light. There are those laws. Before we go into the detail of this derivation, let us first understand this diagram. Okay. So if you see this horizontal line AB, this is my reflecting surface. These are the normals. This point E and F over this reflecting surface. And these rays, these green rays, if you see, these are your parallel incident rays. And these rays are coming from an object which is situated at infinity, somewhere at infinity. And these red rays which you see, these are your reflected rays. Okay. And this incident rays, they are incidenting at this different point. So this ray is incidenting at this point E. This ray is incidenting at this point F. And angle of incidence 45 degrees. And since these rays are parallel, incident rays are parallel, so the shape of the wavefront for all the incident rays is going to be a plane surface. Okay, because we have already studied what are the different types of wavefront. There are three types: spherical wavefront, cylindrical wavefront, and plane wavefront. The plane wavefront is associated for those rays which are parallel to each other. That means when light is actually coming from an object which is located at infinity. So I'm going to be showing you a simulation. But before showing you the simulation, I just first recall Huygens principle because we are going to actually use that principle. Alright. So Huygens principle states that every point over any wavefront acts as a new source of disturbance, secondary disturbance, we call wavelets. Now this wavefront KE you see. So this is incident plane wavefront, and every point over this wavefront will behave as a new source of secondary disturbances. Right. So I will limit myself, I'll restrict myself only to these 2 points, point K and point E. Right. So I'm going to be showing you a simulation where wavefront will be developed from these 2 points, point E and point K. That means light waves are coming out from this point sources. So let's just play this simulation. So as you have observed, that both this wavefront, spherical wavefront, from these 2 points K and E, started to develop at the same instant, right? And they are growing. That means the light which is coming out from these 2 points, point K and point E, they are moving with the speed of the light of the particular medium, whatever medium you choose. So that if I choose the medium to be air, so the light waves are emitting in all the 3-dimensional directions with the speed of light c, which is 3 × 10⁸ meters per second. Alright, so I'll be like playing this simulation. So as you can see, this wavefront is growing with respect to time, and they are moving with the speed of light c. If I see this region, here they are moving with the speed of light. Both these rays will grow. Yes. So now if you see this wavefront which has developed from this point A, so it has taken certain time to grow from this point K to reach point F. Certain time he has taken. Let's say that let T be the time taken by the wavefront developed at K to reach point F. Let T T with the time interval, time taken. And during that same time, the wavefront developed at point E. E has reached, while it was growing, and finally it has reached point Q. And the wavefront has taken the same time T. Okay? And during the same time interval, the wavefront developed at point E has reached point Q. Okay. During that same time interval, this wavefront has also reached point Q. So if I want to show you the reflected wavefront, plane wavefront. So what I'll be doing, I'll be drawing a tangent over this wavefront. I'll be drawing a tangent over this wavefront, and that tangent is going to show you the plane wavefront, reflected plane wavefront, or reflected rays. These are your reflected rays. Okay. So what I'm going to do first, I'm going to hide all these circles, and this is the tangent to that particular wavefront developed on this point Q. So this QF, this line segment QF, is the reflected plane wavefront, okay, for these rays, reflected rays. Right. Now, since the time taken by the wavefront to move from point A to reach point F, and the time taken by the wavefront to move from point E to point Q is same, and both of them were moving with the speed of light c. So therefore, you can say, this distance kf is equal to eq, which is nothing but speed into time, c multiplied by e. Okay. And now what we are going to do, we are going to consider this triangle KEF and triangle QE. Okay. So before going into this triangle, let us clear a few points. Like if you say this is my plane wavefront, incident plane wavefront, and this incident plane wavefront will always be perpendicular to my rays, okay, incident rays, right? So this angle which you see, this will always be 90 degrees. So they are perpendicular to the plane to the rays. This plane wavefronts are perpendicular to your rays. So that's why they are making an angle of 90 degrees. And this angle which you see, this is again 90 degrees, and this angle which you see here, this entire angle which you see, this is the incident angle I. So since this is let's say that this is 90 degrees, because this is wavefront, this is plane wavefront, and this is your ray, they are perpendicular, so this angle will be 90 degrees. And since this is angle I, so this angle will be 90 minus I degree. Okay, so this angle is going to be 90 minus I. And again, this is 90 degree. Okay, so if this is 90 minus I, so this angle is going to be I incident angle. Okay, so that is why this is the angle which you see here. The same angle is the same angle you will see for this particular angle, like K, E, F. Again, this angle which you see, this is your reflected angle of reflection. Now, since this angle is 90 degree and this is your R, this angle which is E, this is 90 minus R. Again, this is again 90 degree. So since this is 90 minus R, so this angle going to be right. We are going to make this two angle equal to each other. So we are actually proving laws of reflection. And very first law states that angle of incidence has to be equal to angle of reflection. Right. So say triangle E E F and triangle Q E F Q E. Now, if you see this triangle EEF and QEF, since this wavefront perpendicular to this ray, therefore this angle is 90 degree. Angle EEF is equals to angle. This angle is 90 degree. Angle FQE, both of them are equal to 90 degree. Again, this distance QF and EQ. QF, both of them are equal. Sorry, KF. KF and EQ. Both of them are equal, which is nothing but CP. And this distance EF. Now, EF is common to both the triangles EF and QEF. Right. Therefore, triangle EEF is congruent to triangle QEF. Right? Now, since these two triangles are congruent to each other, therefore, this angle EEF E E. Okay, so this was K. I'm sorry. So this will be KEF. Angle KEF. KEF is going to be EKF. EKF. KEF. It's not going to be P, it's going to be K. KEF. Right? And QEF. Therefore, angle KEF, means this angle KEF, is equals to angle QFE. Okay. So both of them are equal. So this angle KEF is the angle of incidence I, and this angle QFE is the angle of reflection R. Okay. Therefore, your angle of incidence I is equals to angle of reflection R. states my first law of reflection. We have already said that the angle of incidence equals to angle of reflection. Okay, so this is how now we will be deriving the first law of reflection using wave theory. Most importantly, we are actually using Huygens principle to derive this law. Okay. Okay. So for second law of reflection, okay, if you see this diagram, this incident ray reflected ray and normal, right? The incident ray, reflected ray, and normal all are perpendicular to this plane surface, plane wavefront surface. Alright, all are perpendicular to plane wavefront surface. Okay, all are perpendicular rays. So therefore, all lie in the same surface, or you can say same plane. Same plane. Since all of them are perpendicular to this plane wavefront surface, so all lie. And when we say all, we actually try to mean here is incident ray, reflected ray, and normal. All of them lie in the same plane. Okay, so this is our second law of reflection. So this is how we prove this. Our second law of reflection using wave theory. Okay, thank you.